Okay, let's start the lecture. We'll continue today talking about developing some of the basics, especially for discrete probability spaces or finite probability spaces that we were talking about last time. A quick recap of what we discussed. A probability space, we said, is specified by two objects. One is a space of outcomes, also called the sample space, and the other is some sort of distribution or probability measure, which assigns a number between 0 and 1 to every element of the probability space, and then sums such that the numbers sum up to 1, which we think of as some sort of likelihood of each of these outcomes. And we defined a few terms which using an event, which is just a subset of the outcome space. So it's a set of possible outcomes. And we saw that we, instead of explicitly writing it as a set, we kind of write it in some sort of logical language, or we kind of say that something happens. So instead of saying the set of all outcomes where the throw of a die gives us an odd number, we just say an event is that the kind of the throw of the die returns an even number. We don't always explicitly talk about subsets. And we also define random variables, which are, again, we define real valued random variables. You can also think of random variables taking values in any other space you want, but when they are real valued, we can actually define things like expectation of this random variable, because we can multiply values of this function with our probability distance, sort of values of our probability measures, which are real numbers, and add them up. You can also do this when sort of X outputs a vector of real numbers, or anything which can be reasonably multiplied with real numbers, so numbers between 0 and 1. So then you can define expectation. But if it was taking values in, say, a finite field, then this would not make sense. We define conditioning, which is nothing but restricting the sample space to an event or a subset. And in particular, if you restrict to an event A, you get a new measure, which is the conditional probability measure. And then we can define the conditional probabilities, conditional expectations, etc. And we started talking about this concept of independence, that we say events A and B are independent if the probability of B does not change, whether you condition on A or not. I mean, equivalently, the probability of A does not change if you condition on B. And there was sort of a more symmetric way of writing it, is that the probability of A intersection B is equal to the probability A times the probability of B. Okay, so this is sort of what we talked about in previous lecture. And we said the two random variables X and Y are independent if for every value they can take. So we said random variables X and Y, let's say mapping to real numbers, are independent if for all values they can take, the event that X takes the value little x and Y takes the value little y are independent. So any questions about that? Anything you'd like me to go over again before we continue? Okay, so then let me ask some questions. So I asked you to think about these two things last time. I claim that if X and Y are independent random variables, then whatever is said for probabilities, you can also say that expectation of X times Y is equal to actually the product of expectations. Any We tried to prove this. Any suggestions on how to prove it?
On the left-hand side, you start with the double summation xy times the probability x probability y. Then it splits because the summations can be split.
Sure. So yeah, so we can I mean, it takes maybe one more step to get to this point from the definition of expectation, but we can write the left-hand side as a value x, which is in the range of x, a value y, which is in the range of y, probability that x is equal to x and y is equal to y. Yeah, this is times this value. Yeah, as I said, I mean, starting from the usual definitions of expectation, you may take one step to get to this point. But once you get here, because, and it's important that the x and y are functions mapping to real numbers, so potentially the set of values in sort of in the range can be infinite, but they are functions from a finite space omega, so they can only take finitely many values, because for every element of the space of the sample space omega, they have to take one fixed value, and there are only finitely many elements. And using independence of the events that x is equal to little x and y is equal to little y, you can write it as the product of these probabilities. And once you do that, you can write it as a product of summations. At which point we are done, because this is nothing but expectation of x, and this is nothing but expectation of y. Okay.
It works for omega infinite as well if you have continuous RBs, yes, right?
Yes. So you can do this with continuous random variables, but yeah, I mean, this proof may not make sense, and we'll be a little more careful when doing that. Yeah. Okay, good. Okay, what about the converse? Is it true that yeah, you may need some conditions, like at least things are bounded, etc. But yeah, we'll get to that when we get to continuous random variables. But what about the opposite side? Is it true that if I can say expectation of x times y is equal to expectation of x times expectation of y, does it imply that the random variables are independent? And by the way, for the question on continuous random variables, I mean, in the measured sense, what you're doing here is really sort of applying something like Fubini's theorem. And so whatever conditions you need to apply that theorem is what you need to do this computation. But yeah, we'll get to continuous random variables later. What about the converse? Yes, no?
Not true.
PFC? Sorry?
Not true, doesn't hold.
Right, so yeah, I mean, you can construct even relatively simple random variables which don't take too many values to see that this can be false. So, and in fact, we can sort of even think about the stock market example that we had. So let's say X is equal to 1 or -1 with probability half each. And let's say Y is equal to 2 when X is equal to 1, and pick your favorite value. So 5 when X is equal to -1. Okay. Sorry, maybe not. Sorry. X is equal, Y is equal to 2 or -2 with probability half each when X is equal to 1, and 5 or -5 with probability half each when X is equal to -1. So the expectation of X times Y will be 0. The expectation of X is 0 and the expectation of Y is 0. So you will actually have equality, but it's certainly not the case that they are independent. In particular, the event that X is equal to 1 and Y is equal to 2 are dependent, dependent events. If I condition on X being equal to 1, the probability of Y being equal to 2 is half, otherwise it's 1/4. So for example, we can check that the probability of Y is equal to 2 is 1/4, because depending on the value of X, which happens with probability half each, Y is 2 or -2 or 5 or -5. But the probability of Y is equal to 2, given that X is equal to 1, is half. So, I mean, yeah, probably there can be an even simpler example which demonstrates this. But in general, expectation being product of expectations doesn't guarantee us independence, even for random variables, basically taking 2 or 3 values, so relatively simple random variables. Does that make sense? Any questions? Okay, and we can also talk of independence of many random variables or independence of many events, and there can be actually many different notions of what it means for a collection of events to be independent, depending on what application we have in mind. So the stronger notion, which is called mutual independence, is kind of generalizing what we did for 2 events to a set of n events. So for 2 events, we said that the probability of A intersection B is equal to the probability of A times probability of B. And here, if you have n events, you say the same thing for any subset of 1 to n. So you look at a bunch of events, look at their intersections, or look at the corresponding products of probabilities, they should be equal. Okay. And for random variables, we do what we did before, that we look at the events that the first random variable takes value x1, second variable takes value x2, and so on, and say that all these events are mutually independent according to the above definition. Okay, so that's one way of doing it. Depending on the application at hand, I mean, yeah, and this is what we will usually see, but depending on the application at hand, we may be able to get away with kind of restricted notions. So in general, maybe we can require every pair of events. So maybe we don't really say that what happens for probability of A1 and A2 and A3, but we just say that probability of A1 and A2 is equal to product of probability of A1 times probability of A2. Same for A2 and A3, same for A3 and A1, and so on for every pair. But we don't really talk about 3 events at a time. And then that notion of independence is called pairwise independence. And just because mutual independence is asking it for all sets and pairwise independence is only asking for some of the subsets, it's kind of makes sense. It's sort of clear that pairwise independence is a weaker notion. So there can be events which are pairwise independent, but not mutually independent, or there can be random variables which are pairwise independent, but not mutually independent. So as an exercise, find 3 random variables, x1, x2, and x3, which are pairwise independent. But not mutually independent. And I mean, finding good random variables which satisfy weaker independence properties is sort of like a whole area of research. And in general, kind of constructing things which have a lot of independence requires access to a lot more randomness, and there is an entire sort of area of research around how much randomness do we really need to do something, whether we actually need any randomness for computation or not. And these sort of questions come up all the time. There are many notions of only limited amount of independence. This is one. And I mean, you can of course also say that I will only look at subsets of size at most k, and this is called k-wise independence. So this can be a parameter. And there are various kind of approximate notions as well, that maybe I'll look at sets of size k, but I won't really require equality, but I will allow a little bit of error, etc. So we'll not discuss those, but I just want to emphasize that there are many possible notions of independence or approximate independence of random variables. And depending on the application, you may want to choose which serves your purpose better. And I mean, and you can see from the exercise, once you think about it, is that maybe it's easier to find random variables which are pairwise independent or construct them, even if they are not mutually independent. Okay. Any questions? Okay. The last thing I want to say in this sort of basics part is to say that, I mean, whatever we did for finite outcome spaces or finite sample spaces essentially generalizes as such to spaces where we can write summation over omega in omega. And you can write a summation when your space is countable. So you can sort of sum over the first element and then the second element and the third element and so on. And so you can you have a mapping from the space to natural numbers, and you can say this is the first element of my space, this is the second element, and so on. And infinite summations are limits, so one has to be careful about whether this converges or not. But other than that, the same definitions, essentially the same theory kind of carries over when you have a countable sample space. When it's not countable, like when your sample space is any real number between 0 and 1, this is not a countable space. And then we need to work with a bit more care, and then we'll get to that later. But for countable, as long as you can sort of say something about convergence, you're fine. Any questions? And together, this sort of finite and countable is what is referred to as discrete probability spaces. And so what we said so far applies to discrete probability spaces in general. And when you don't have countable spaces, then you need to work with a bit more care, and we'll get to that in a couple of lectures. Okay. Now let's, and so before we get into some applications, one other thing I wanted to do was introduce some sort of common random variables and some concepts related to, in particular, I'll define the concept of variance, which you'll need for the homework. But let me just define some sort of commonly encountered random variables. Okay. A Bernoulli random variable is just a simple random variable which is either 0 or 1, and it's specified by a parameter p, which we take to be the probability that it's equal to 1. First things first, I mean, so I kind of switched gears a little bit. Instead of talking about random variables as a function from some space and so on, I just started saying that this random variable takes some value with some probability, some value with some other probability. Can you tell me what space omega should I consider to define this random variable? So can I write it as a function from some space omega with a measure on that space omega in the way we have been talking about so far, rather than this funky way? So I want to write x as, in the kind of things we developed so far, that I want to write x as a function from omega. I know it only takes values 0, 1, so maybe a function which is 0, 1. And I want to construct an omega, and I want to construct a probability measure which maps omega to sort of numbers 0 to 1. Can you give me an omega like that?
Would it maybe be F2, like the field 2?
It could be F2. I mean, yeah, so the values of the random variable are 0 or 1, but for the values, we should be careful to think about them as real numbers, because we want to add them and we want to take expectations, and F2, things in F2 cannot be multiplied with real numbers and added. But yeah, the omega itself can be F2, or in particular, it can just be any space with 2 boxes, really. You can think of them as F2 or not. And we will sort of, these 2 boxes, let's just call them omega 1 and omega 2. And we will say that the value of nu of omega 1 can be p. Here it can be 1 minus p. And we can define x of omega 1 to be 1 and x of omega 2 to be 0. So we can consider any omega with 2 elements and do this. It can't be 1 element, because then a function defined on a space with 1 element will only take 1 value, and x has to take at least 2 values. But it doesn't have to be limited to 2. So the same random variable can be defined on a different omega. And again, it's really a question of modeling what sort of models the problem at hand. And so you could have considered a sample space with 4 boxes. You could have said that the value on these 2 boxes is 1, and the value on these 2 boxes for x, which is a function, sort of for each box writes down a number, is 0. And mu can be anything as long as, let's call these omega 1, omega 2, omega 3, omega 4. Mu can be anything as long as mu of omega 1 plus mu of omega 3 is equal to P, which is what we want, the probability of X equals 1, the event X equals 1, which is kind of denoted by the green shaded region, should have the probability P. That's the one condition we want. And the remaining two boxes can have the values of nu summing to 1 minus P. So it could have been some other probability space. And the values of nu you could have chosen in whatever way you want. You could have set P over 2 in each of the two left boxes, 1 minus P divided by 2 on each of the two boxes on the right in omega 2 and omega 4. And these are both perfectly valid spaces. It's a question of what suits your application. Since we are just considering one random variable right now, we can just go with the space with the two elements. We will see in a minute that when we might want to define many different Bernoulli random variables on the same space, and then it might actually make sense to consider a larger omega to define even Bernoulli random variables. Okay, we'll get to that in a minute. The expectation here is we can write it as the probability that X is equal to 1 times the value 1 plus the probability that X is equal to 0 times the value 0. The probability that X is equal to 1 is P, and this term is 0. So the expectation of a Bernoulli random variable is P. This is something which is very simple computation, but surprisingly useful, because often we will need to calculate probabilities. If we have a Bernoulli random variable, we can think of a probability as an expectation of the random variable. And once we get to expectations, we get to use things like linearity of expectation, etc., which are surprisingly powerful and can simplify computations a lot. So just the simple fact that the Bernoulli random variable with parameter P has expectation P, well, it takes two values and the other one doesn't contribute, it's 0, is very simple, but surprisingly useful. And then we'll see later that it comes up all the time. Okay. One other concept which I want to define here is the variance of a random variable. A variance is nothing but an expectation of a slightly different random variable. So let's say the expectation of our random variable is some number mu. In this case, I mean, mu is P, but I'm just sort of denoting in general by symbol mu. And then for any random variable, the variance of the random variable is the expectation of X minus mu whole square. Okay. If you think about it, X minus mu whole square is just some other random variable. You can call it Y. If X is a function on omega, it takes values, some value for every element of the sample space. Then X minus mu whole square is also a function. It takes also some value on every element of the sample space. So it's just another function. It's just another random variable, and I can define its expectation. So the variance of X is another random variable, and as the name suggests, it sort of captures it's some measure of how much X varies from its expectation or the typical or like the average value. It need not be typical. For example, the random variable X, a Bernoulli random variable, the value P is not typical. In fact, it's never equal to. But it's just a question of how much does the value deviate from the mean or from the mean or expectation. All of these are different terms we will use for the expectation of a random variable. Okay. There is another way of writing it, which we can obtain by linearity of expectation and just opening up the box. So you can write it as X square minus 2 mu times X plus mu square. And then use linearity of expectation to write it as expectation of X square minus 2 mu times expectation of X plus mu square. Expectation of X is another mu. So when you plug in expectation of X is equal to mu, this can also be written as expectation of X okay, Or another way of writing it is expectation of x squared minus mu was nothing but expectation of x itself. So it's expectation of x squared minus expectation of x whole squared. Okay, that's just another way of computing the variance. So this is just the definition of variance for a random variable. This is true for any random variable. I didn't really use anything about the Bernoulli random variable yet. Okay. And because we defined variance as the expectation of square of something, it makes sense that this quantity is greater than or equal to 0. So expectation of x squared is greater than or equal to expectation of x whole squared. Okay, this is a fairly useful inequality that we will use all the time, and as an exercise you can also try to prove it using Cauchy-Schwarz. I mean, we already gave one proof of it, which is just written here, but again, a relatively simple inequality. Okay, so since I kind of filled this page up, let me use a new page to compute the variance of a Bernoulli random variable. Any questions about this, by the way? So we said for any random variable, variance of x is equal to expectation of x squared minus expectation of x whole square. And we were interested in the Bernoulli random variable where x is equal to 1 with probability p and 0 with probability 1 minus p. So now let's calculate the two terms that appear. We've already calculated the term here. What comes inside the bracket is p, so the bracket just computes contributes p square, and we want to compute the first term. Any guesses on what it is? I mean, yeah, we can calculate it. It's very simple to just sort of plug in the formula for expectation. But actually notice that x is either 1 or 0. 1 square is always 1 and 0 square is 0. So x squared is equal to x as a function. On every input, the value x squared takes is the same as the value x takes. So for a Bernoulli random variable, this is only true for a Bernoulli random variable, by the way. It's not true in general that x squared is equal to x. Bernoulli random variable only takes values 0 or 1. And when it takes value 0 or 1, it's true that x squared is always equal to x. So this whole thing is also p, which is nothing but the expectation of a Bernoulli random variable. So the variance is p minus p squared, or can be written as p times 1 minus p. Okay, and so the closer p gets to half, the larger this quantity is. The farther p gets from half, the closer to 0 it is, or 1 it is, the quantity is smaller. Okay. Any questions about this? So, computation probably all of you have done at some point, but it's kind of, again, a nice fact to remember that the Bernoulli random variable x square is equal to x. So it simplifies a lot of computations because, well, we know expectation of x in most situations. Okay. Now let's get to what is called a binomial random variable. A binomial random variable is a sum of, it is defined as a sum of independent Bernoulli variables, and how many Bernoulli variables we are taking, and what is the probability that each of them is 1 or 0 are parameters. And so here, these are all identical Bernoulli variables in the sense that they have the same probability of being 1, which is p, and the same probability of being 0, which is 1 minus p. Okay, but they're independent, which means that whether I condition on x1 being 1 or 0, it doesn't really change the distribution of x2. Okay, does that make sense? Okay, and here, to sort of define this random variable z sub n over a space omega. Oh, sorry. To define it over a space omega, what I need to do is, or at least, I mean, one way of defining it is to say that I have to define all these random variables x1 to xn as functions on the same space, because there are some outcomes, and this outcome tells me what happens to x1. It also tells me what happens to x2, and so on. And then it tells me finally what happens to z sub n. Okay. This is not necessarily the only way of defining it, but that's one common and convenient way of defining it. So I can have an omega which has 2 to the n possible outcomes, and I can assign a measure nu to every outcome in here. I can think of these outcomes as actually just strings in 0, 1 to the n. Which tell me what happened to the random variable x1, what happened to the random variable x2. So this omega has enough information so that x1 to xn can all be written as functions on this space omega. You can think about what nu should be if I want to define them as independent random variables. But actually computing the expectation is already very simple, sort of without necessarily having to know everything about omega. Okay. So we know that expectation, assuming you can write down some omega and define zn and x1 to xn on the same omega, expectation follows this linearity of expectation rule that expectation of zn can be written as summation over I from 1 to n expectation of xi. Okay, and each xi we know is very simple. So this is what I think I also mentioned last time, that just like maybe when thinking about the stock market or whatever, the sort of a very complicated random variable can be sort of split as a sum of relatively simple random variables which only depend on small number of things, and their expectations might be very easy to calculate. So here I can know that the expectation of xi is just p because it's a Bernoulli random variable, and we already solved this. And so the expectation of the binomial random variable is n times p. That makes sense? Okay. Now I'll ask you to think about the variance of this random variable. So let's take maybe 2 minutes to try and compute. We'll take a 2-minute break, and meanwhile you can try to think about how to compute it, and then we'll continue. All right, did anyone figure out the variance? Okay, no one is answering. Is it already too easy and everyone has seen this, or is it something which is not clear how to do? So, right. At least if it's not clear, speak up. But otherwise, we can go over this quickly. Yeah.
I would appreciate an explanation of this.
Yeah. Okay. Now let's do that. So, I mean, in fact, yeah, I want to illustrate a couple of things which come up in computation of this variance, which are very useful techniques in general. So, we saw that for any random variable, the variance can be written as expectation of the random variable whole squared, no, the random variable squared minus the expectation of the random variable, the entire thing squared. Right? This is the same computation we did. It's just the definition of variance for a random variable. And the second quantity we have already figured out how to compute. Right? It's the expectation of Zn we know how to compute, so we can square it. It's the first quantity which is not clear how to calculate. And we can write it as expectation of, so Zn is nothing but summation over I xi, and we are trying to square this. And we can open up the summation and write it in terms of when I is equal to j, when I is not equal to j. Okay. So far, yeah, I mean, all we have done is just sort of expanded a summation, expanded a square. Now we have linearity of expectation, so I can write it as summation over I, expectation of xi squared, plus summation over I is not equal to j, expectation of xi xj. Okay. Can anyone tell me what expectation of xi square is?
Same as we did before.
Right, so it's a Bernoulli random variable. The Bernoulli random variable is equal to its square, so the expectation of xi square is just p. And xi and xj are independent. So expectation of xi xj is equal to expectation of xi times expectation of xj, which is p times p, or p square. Okay, so now let's just collect terms. So we get n times p plus n times n minus 1 times p square. Okay. And once we have these, we can continue on the next page. So we said the variance was equal to expectation of Zn square minus expectation of Zn whole square. The first term we just computed is equal to n times p minus n times n minus, sorry, plus n minus 1 times p square. And the second term, we computed the expectation already, it's n times p, so it's n times p whole square. Okay. And you can rearrange it. It's yeah, you can cancel the n square p square term. You will be left with n times p minus p square, or n times p times 1 minus p. And notice the p times 1 minus p was actually the variance of a single binomial random variable. So actually, this is equal to the variance of x1 all the way up to variance of xn. And you can prove this in a couple of different ways. But first thing I want to notice is that on the previous page, the only place we used independence was this line. And we only used independence of two random variables at a time. We never talked about independence of x1, x2, x3 together, only two of them. So all we used was pairwise independence. So the computation we did actually works in general, and the following maybe is a slightly easier way of doing the same thing, which also generalizes. So instead of sort of computing the variance the way we did, let's look at the other definition of variance, which is Zn minus mu, where mu was whatever is the expectation of our random variable. So it's expectation of Zn. So this way of writing it is a little confusing because there is an expectation inside and expectation outside, but expectation of Zn is a number. We can subtract it from Zn and square it. This is what we call mu, and I was just using mu to sort of avoid this confusing notation with the two expectations. But the second expectation is kind of already done. We are not taking anything over omega. It's just already computed and it's a number. Another way of writing it is just expanding the summation inside, and what you will get is expectation of summation over I. So this is something to check, but you can write it as summation of xi minus expectation of xi. The whole thing squared. I'm just sort of writing the Zn as summation of xi and using linearity of expectation inside. And let's call these random variables yi's. And yi is just xi minus some fixed numbers. So you can check that if xi's are independent, so are the yi's. And then by kind of opening up the square, you can write it as summation over I expectation of yi square plus summation over I and I not equals j expectation of yi yj. And again, it'll take a minute to just see that I can write it as a product of expectation of yi times expectation of yj. Which is 0 because of the way we defined yi is we defined it as xi minus expectation of xi. So when you take the expectation again, it's 0. So that's just another way of computing the same quantity or the same variance. But this yi has a nice interpretation for the expectation of yi squared. Yi is just xi minus expectation of xi. So the expectation of yi squared is just variance of xi. So without really plugging in any numbers, we can prove that if we have z as x1 plus xn, then variance of z is equal to summation over I times the variance of xi. And moreover, I didn't really use anything in this second way of doing the proof. I didn't really use anything about the definition of xi's except that they were pairwise independent. Okay. I didn't even use the fact that they are identical, they have the same binomial parameter. I didn't even use the fact that they are binomial in this second computation. So this is actually true for any collection of pairwise independent pairwise independent random variables x1 to xn. More generally, the binomial random variable, the Bernoullis that appear are just a special case with even more interesting properties, that they're mutually independent, really. Okay, any questions about this? Okay.
Really quickly, could you, sorry,
Yeah.
could you explain why the expectation of y sub I is 0 again?
Yeah, of course. So let's do that. So what was y sub I? Y sub I was defined to be expectation of, y sub I was defined to be xi minus expectation of xi. Expectation of xi is a number like 0.3. So you can think of it as, so I'm just subtracting some number from xi. And now let's think of expectation of yi. By linearity of expectation, I can write it as expectation of, what I'm looking at is this quantity. And by linearity of expectation, I can write it as expectation of xi, the first term, minus expectation of xi. But expectation of xi is already a number. It's, if I take its expectation again, I get back the same number. So expectation of xi is just the same thing. It's just expectation. And so this is 0. Does that make sense?
Yes. Okay. Thank you. Thank you.
Good. Yeah. I mean, these are simple calculations, but they're still kind of nice things to observe in each of them. In particular, the fact that variance sums up for any collection of pairwise independent random variables is very useful. And in general, this technique, which we kind of exploited in 2 ways of trying to compute the variance by looking at, now we are looking at a square quantity, so we can't quite look at one variable at a time, but we can look at 2 of them at a time. And if we know something about how 2 of them interact, it helps us a lot in computing variance. In particular, if they are independent, it gives us a really simple way of doing it. And we'll see later this sort of same computation appears again and again in many different guises when you kind of analyze 2 random variables at a time. Okay. The third random variable I wanted to define is a Bernoulli is a geometric random variable. Okay. And this is slightly funnier to define. So it's still defined in terms of independent Bernoulli random variables, but there are 2 issues. One, it's not a sum or anything. It's defined as in some weird function over these random variables. And secondly, there are infinitely many of these Bernoulli random variables, not just n of them. Okay. So I'll define a thought experiment in a way, and then we'll see how to formalize this. But let's say we had an infinite sequence of IID, which is just a short form for independent and identically distributed. And by the way, when I say independent without any context, it's mutually independent. That's the most used notion. If I'm talking about some other specific notion, I will sort of say it explicitly. Okay. So we are looking at, let's say, a collection of n independent and identically distributed Bernoulli random variables, and it's often convenient to think of them as coins. So a Bernoulli random variable is something which is 1 with probability p, 0 with probability 1 minus p. Think of it as a coin which comes up heads with probability p and tails with probability 1 minus p, let's say. So I'm sitting at my desk, probably nothing better to do. So I'm just trying to toss coins one after the other. And let's say it's the same coin, which always comes up sort of heads with probability p, tails with probability 1 minus p. And I'm going to sort of keep tossing it again and again. Yeah, maybe I don't have anything better to do on a Thursday. So, and y is the first toss at which I see a heads. Okay. So toss it the first time, maybe I saw heads, great, y is equal to 1. Then, or maybe I kind of tossed it the first time, I got a tails. Then I tossed it again, I got a tails. Then I tossed it again, I got a tails. Then I tossed it again, I got a heads. So y is 4. Okay. So y is the first time I saw the value 1 as an output of this Bernoulli random variable. The first time I saw heads come up when I was tossing this coins, which I was willing to toss an infinite number of times, because it's possible that I keep tossing them and it just keeps coming tails and tails and tails again. There is some positive probability of this happening, at least for any finite number of tosses. Okay. Is the context clear? It's the definition of the random variable. Okay, that's okay. Couple of things about it. It's first, any guesses on how to define omega? How to think of this random variable y as a function from a space omega to I should say, I mean, it's not that sort of I just like sitting on Thursday mornings and tossing coins for a long time. This kind of random variable is used to capture a common process where we are trying to kind of solve some problem or trying to look for some particular event to happen, but it's a random thing, so it may not happen, and we might try running our algorithm many times, or we might try kind of looking for the object we are searching with many attempts, and it's sort of this random variable kind of captures how long do we have to wait till we can expect some success, or till we can actually expect to find what we are looking for, and we'll see other examples of this. So this is a common way of modeling sort of repeated attempts at doing something which may or may not succeed, okay, or another variants of that. So, all right, any guesses on how to think of omega?
So this could be totally wrong, but if I'm thinking of, so I have a box with, we split it in half.
Okay.
Where the left-hand side is that it comes up 1 the first time.
Mm-hmm. Okay.
And then the right-hand side, we have to split that in half as well, that it's 0, 4, and then the next toss is 1.
Uh-huh.
And then you have to split that box again. So you kind of get split it like an infinite number of times.
Good. So yeah, infinite but countable. So so that is one. I mean, you kind of already sidestepped the trick question that I was actually going to give, because one common answer is we can think of an infinite sequence of zeros and ones representing the outcomes of all these tosses, but infinite sequences of zeros and ones are not countable. So that's and we can go to that definition, but not just yet. What you gave is actually a countable set, so it already works. So we can think of another way of saying what you were saying is we can think of this sequence where maybe the first toss came up heads and we don't have to worry about anything else, right? Or the first one came up 0 and we are in the second half of the box that you were mentioning. And the second half of the box, we kind of split it into 2 parts, or at least 2 parts, where the first one was what if the first toss came up 0, and the second one. And then we can think of what happens if we got a 0, 0 and a 1, or we got a 0, 0, and we can keep doing this, right? Is that roughly what you had in mind?
Yeah, that's what I was trying to get across.
Okay, great. So, and notice that this is actually in one-to-one correspondence with the set of natural numbers, because the position of the 1 is defining a counting on these, right? So the 1 is in the first position or the second position or the third position. It's just a string of zeros followed by 1, 1, right? Because when we notice the first heads, we stop, and that gives us sort of a natural number. So this is a countable set. Okay. So it's a nice story to sort of define it in terms of this infinite sequence of coin tosses, which probably But yeah, maybe the outcomes of all those infinitely many coin tosses are not necessarily required to define omega, and this is a countable way of defining an omega. I'll leave it as an exercise to think of what nu should be. Actually, maybe let's compute it. It's simple enough. So it's sort of trying to capture our intuition for these independent coin tosses. The probability that I tossed x1 and it came up heads is p. The probability that I kind of tossed the first coin, it came up tails, is 1 minus p. And because of independence, the probability that the second random variable came up heads, conditioned on the first one coming up tails, is still p. So it's 1 minus p times p. Similarly, this is 1 minus p square times p, and so on. Right. So that tells us that the probability that y is equal to some number k is equal to 1 minus p to the k minus 1 times p. So that's one way of computing the variance. So that's one way of computing the probabilities.
One question I have.
Yeah.
So y goes from this space to
natural numbers.
To natural numbers, or should it just go to 1? No, yeah, natural numbers. Okay, when you saw the edge, yeah.
Yeah. So I mean, in particular, y is a random variable for which I don't have any bound on how large it can get. It's an unbounded random variable. In expectation, we'll see what it can be, but it might be a billion or a trillion or whatever, depending on how long I was willing to toss the coins for. Since I committed to tossing an infinite number of them, it can be as large as it is. Okay. Now, we can compute expectation of y using what we just saw in terms of probabilities. So we can say that now we write this infinite sum. We can say, and we will have to be careful about its convergence. And we can say that the probability that the random variable is equal to k is 1 minus p to the k minus 1 times p, and this is the value. So we are using the expression for expectation that we derived, which was the probability that the random variable is equal to k times the value k. Or maybe I've written k first. Okay. And we can compute this. We can check that this series converges and it's equal to some number. But there's also another way of computing this expectation, which is a more slick way and also illustrates a technique which is useful. So recall that we had this law of total probability, or total expectation, where we said that if you have an event A, then expectation of y can be written as expectation of y conditioned on A times the probability of A, plus expectation of y conditioned on A complement times the probability of A complement. Okay. And this is actually sort of a very useful thing to think about for this kind of processes which are infinite or which can go on forever. So it sort of helps us simplify things quite a bit. Expectation of what y is what we are trying to compute. And let me now define A as the set of all outcomes where x1 is 1. Okay, so the first coin comes up heads. It may or may not. So we will consider A and A complement both. But this is just an event that I'm defining. Okay. And this gives a relatively simple way without really bothering about this sort of series to compute things. Because the probability of A, or the probability that x1 comes up heads, is P. If I tell you, if I condition A, or if I restrict myself to all outcomes where the first coin was heads, which is only one outcome in this particular space, then y is 1. Right? If the first coin came up heads, I just don't go further. The probability of A complement is also easy to know. It's just 1 minus the probability of A. And you can check because all total sum of all probabilities is 1. And now the interesting thing is to understand what happens to Y when I condition on A complement. So if I tell you that the first coin was tails, can you say anything about the behavior of the random variable Y if I condition on this event, or I sort of just change myself to looking at the complement of it? So I'm just looking at this space now. Conditioned on this event or conditioned on looking at this part of the space, what happens to the random variable Y? Okay, this one is a bit of a trick to see, but I claim that this is equal to, it has the same distribution as the random variable Y plus 1. Because I told you that the first coin came up tails. Okay, so I'm going to be living in this space A complement, and I'm going to be dividing all probabilities by the probability of A complement, which is 1 minus P. So I will get the Y sort of this probability that Y conditioned on A complement or sort of Y is equal to 2 conditioned on A complement will be 1 minus P times P divided by 1 minus P, or rather P, which was the probability that Y is equal to 1, and so on. So you can see that all the probabilities will just be shifted. The probability that Y is equal to K conditioned on A complement will be the same as the probability that Y is equal to K minus 1. And intuitively, this makes sense because if I tell you that the first coin came up tails, the random variables Bernoulli's were independent. So the process just restarts basically, and you lose one trial. So whatever you expect to happen later is just kind of one more than what you were expecting before, if you have this knowledge that the first coin came up tails. Does that make sense? Okay, stop me if something is not clear. But if we do that, then the computation becomes very simple, because we get that expectation of Y is equal to P plus 1 minus P times the expectation of Y plus 1. And if you move things around and solve for expectation of Y, you get that the expectation of Y is just 1 over P. Okay, so that's another way of computing. I mean, you can compute it from the first expression and check that this sums up to this series, that the limit is 1 over P. Or you can compute it in this way without having to sum up series by noticing this fact about the distribution of Y conditioned on A complement. I mean, yeah, whichever you find more convenient, they're both fine. I'll leave it as an exercise to compute the variance of this random variable. Okay. Any questions? Okay, now let's see some, I mean, by now we have kind of most of the basics. So now in the next lecture, I'll try to do some applications of the basics before we develop new concepts. One very simple application is a setting which is called coupon collection, which is again the same sort of thing that we were talking about with geometric random variables, that you're trying to do something and you want to see sort of what is how long does it take till you succeed at doing whatever you're doing. But now what you're trying to do is a bit more complicated. It's not that it's just yes or no, or you're trying to look for heads or tails. But what we're trying to do is collect n type of items or n types of coupons in the problem. And this can be, again, like we are trying to look at data sets and we want to wait till the data set is rich enough. So we have kind of basically some notion of what all we want before we start sort of processing the data, and maybe it's in different things, not just one. Okay. And again, in an idealized setting, let's say that at every step we get a coupon of a random type or an item of one of these random types. So let's say n is equal to 3, and we have sort of coupons which are maybe red, yellow, and green, and maybe what do we put, traffic lights. But I guess we get a random one at every time, and sort of we are waiting and we want to find what is the first time when we have coupons of all 3 colors or all n types. Okay. So T is sort of defined in this kind of infinite sort of way that I want to find out how long does it take before I get all types of coupons. Okay. And the goal is to compute the expectation of T. Is the setting okay? And yeah, Kyle, did you have a question?
No, I was just going to say it was good.
Okay. And this sort of thing, again, as I said, can be used to model sort of a process where we are waiting for few things to happen and their outcomes are random. But it's not just one thing that we are waiting for it to happen. Okay. And here again, it's easier to think of a random variable as a sum of simpler random variables. So and then we will try to use linearity of expectation, which you already said before, where we will define xi to equal to okay. So when we start, we don't have any items, so we have 0 types of items. Okay. X1 is the time it takes us to get to sort of having an item of at least of one type. Okay. X1 will be 1 because the first time we see something, it will be one of these n types, and then we will have an item of one type after one time step. Okay. So X1 is just a funky way of saying the number 1. X2 is the time it takes us to go from one type of item to 2 types of item. So after time 1, we try our luck again. Maybe we get back the same thing we had the first time. So we are still at one type of item. We don't have 2 different types yet. Okay. So X2 is the time we have to wait after we have one type, not at least, after we have exactly one type, to go to 2 types of items. X3 is the time we have to wait to go from 2 types of items to 3 types of items. And these are not necessarily, I mean, it's sort of, it's not a priori clear how these random variables kind of depend on each other or not. I mean, yeah, can think about it more, but in some sense, to compute expectation of T, we don't even need to think about it. So yeah, all we need to convince ourselves is of the fact that T is equal to the sum of these times really, because well, we don't go from sort of 0 to n types in a jump. At every step, we only get 1 type of coupon. So the number of types we have only increases by 1 at a time. It might take a long time to go from 3 types to 4, but we can only go from 3 to 4. We can't go from 3 to 5. And once you have this, it's, I mean, linearity of expectation tells us that to understand the expectation of T, we just need to understand the expectation of Xi. And each Xi is actually a very nice random variable. Can anyone say what it is?
I think xi would be geometric with p n minus I over n.
Right. So xi is geometric. That part, let's see first. So, I mean, xi is just kind of waiting for a yes or no kind of event to happen, right? So we have I minus 1 types, right? And we are just kind of going to the next time step and see what we get. If it is anything different from what we have I types. So it's just saying that, okay, how long does it take till we get anything different from the types we already have? So that's exactly what a geometric is. It's one kind of thing which can either end in yes or no, and just how long do we have to wait for to get a yes or a success at something we are trying. So xi is a geometric random variable. And now let's see what is the probability of success. Right. So we have I types or I minus 1 types already. So if we get anything different from what we already have, which we will get with probability of the total number of things different from what we have divided by n, then we succeed. And at every step, these are identical trials. So it's just a geometric random variable with parameter n minus I plus 1 divided by n. And so expectation of xi is very simple. It's 1 over the parameter, or n minus I plus 1. And once we know that, the expectation of t is also very simple. So the first term is n divided by n minus 1 plus 1, so it's really just n. The second term is n divided by n minus 1, n divided by n minus 2, all the way up to 1. Yeah. So the expectation of this random time t is very easy to compute. I mean, we know even more about what it is. It's roughly n times ln n, and actually it's n times ln n plus some constant times n, where this constant is also known asymptotically and so on. It's called the Euler's constant, etc. But it's roughly n log n, or n times ln of n. And that is again a fact that has a lot of applications. And in general, this method of sort of splitting a time where we are waiting for many different sort of things to happen into times when we are kind of just waiting for one thing at a time is very useful, and just a simple application of linearity of expectation, but in sort of surprisingly useful and sort of analytic tools. Okay, I'll stop here for today. We'll continue more with different applications in the next lecture, and you should have everything you need to solve the homework at this point. I'll stay on after the lecture in case you have any questions.